Welcome back to our cutting edge session, a report from the cutting edge, solving the world's greatest problems with the world's deepest tech. I'm Tabitha Goldstorff, co-founder of CogX, and it's a delight to be welcoming you from wherever you are in the world today. Don't forget to check out the expo on our platform and drop a line to some of the brilliant organizations, make some connections and continue the conversation. Now, we all know how intelligent nature is, but yes, we do often forget it. It provides us with an abundance of unique materials and intelligent systems. And now more than ever, we need researchers, scientists, innovators, businesses coming together to learn from it. Work with it, not against it, in order to figure out new methods of problem solving, especially in the fight against the climate crisis. And that's why, for this session, we'll be exploring the extraordinary area of biomimicry with a leading edge organization based in the United States, none other than the Biomimicry Institute. So on that note, it's my absolute pleasure to hand the reins to Biomimicry Institute's Entrepreneurship Director, Jared Yarnell-Shane. Jared, are you there?
I am
Brilliant.
here.
Thank you so much. Have a wonderful session and I will see you at the end.
All right. Thank you so much, Tabitha. And I'm excited to be sharing biomimicry with all of you today. And I want to start by saying that biomimicry is derived from Greek. We have bios, meaning life, and then mimesis, which means to imitate, to copy. And really, since the dawn of civilization, humans have been not only learning about nature and observing nature, but learning from nature. We've been learning how we can adapt materials, systems, even chemistry to help meet some of our problems and design needs. So at the Biomimicry Institute, we are trying to bring back this practice of how can we learn from nature, not just about nature, to solve some of our global challenges. And when we learn from nature, we oftentimes create solutions that are better. They're just simply better because they've gone through billions of years of evolution, which sometimes we compare to research and development, although it's a bit passive. But at the same time that they're solving human challenges, they are also usually inherently sustainable. They're better for the environment. And to shine a spotlight on biomimicry, I wanted to tell you about one of the groups that we work with through our $100,000 Ray of Hope Prize, which is our annual startup competition. And if you can put on the picture of eConcrete here, great, thank you. So this was the recipient of the 2020 prize. And what you can see is their concrete block in the water on your left, and then about a year later, the same concrete block covered in marine life. So this company, founded by two marine biologists and based in Tel Aviv, what they saw were these pristine oceanfront ecosystems and coral reefs that were just being decimated as humans were building concrete marinas and seawalls and other protective barriers as we face the threat of ocean level rising and extreme weather events. And these marine biologists thought to themselves, well, there has to be a better way. How does nature encourage resiliency and growth? How does nature protect itself? So they have three different kind of design concepts that they brought into their product. On the macro level, they recreate forms such as tide pools and other kind of macro level design structures that are found in the natural world. Zooming in a little bit, they noticed that in nature, it's very rare to have a completely smooth rock face. And ocean life has adapted to live in those crevices and holes and pockets in the rock face, but are completely smooth concrete surfaces that just doesn't provide a habitat for any animals to live. And then zooming in on a microscopic level, the concrete that we were using in marine infrastructure was essentially poison to these marine creatures, and it didn't encourage growth. So they have a proprietary admix that they add into their concrete, which actually attracts and encourages this marine growth. Now, this was not designed, but coincidentally, by going through this process, by building these marine structures and attracting living creatures, they actually strengthen over time through biocalcification and bioprotection. So not only can these systems compete on an economic and structural level, but they actually gain strength and gain resilience over time, protecting humans and the local species. So we're going to talk about a couple other examples of biomimicry throughout this talk. And I'm excited to introduce just a fantastic panel representing research and academia, entrepreneurship, and kind of biomimicry as a whole. What does the future of our planet look like if we all can bring biomimicry into our practice. So I'm going to introduce our panel now. So first up, I'd like to introduce Cece Liu, the CEO and co-founder of Metalmark Innovations, which is a spin-out company of Harvard's Wyss Institute. Cece spent over 17 years in clean tech and sustainability, entrepreneurship, venture investing, and joined Metalmark on their quest to bring clean air to us all, and to clean up our polluted air. Then I'd like to introduce Claire Yanish. She's a keynote speaker, futurist, regenerative design consultant, and innovation advisor. She is the director of Biomimicry South Africa and created the online course Learn Biomimicry to help practitioners of all types, students through professional engineers, to bring biomimicry into their day-to-day practices. And then finally, I'd like to introduce Dr. Tak-Sing Wong, who is an associate professor of mechanical engineering and biomedical engineering at the Pennsylvania State University, where he leads the Wong Laboratory for Nature-Inspired Engineering. Dr. Wong is also the co-founder and CTO of a startup company, Spotless Materials, and we created this short video to tell you a little bit more. So if we could roll that video.
This carnivorous pitcher plant has a particularly gruesome party trick, a highly slippery outer rim which causes insects to slip into a tube full of digestive juices. This super slippery rim, called a peristome, consists of a micro-textured surface which becomes incredibly slippery when it gets wet. This microtexture is formed from overlapping epidermal cells, which cleverly directs insects to slip inwards and not out of the plant. Now, a company called Spotless Materials is designing its own coatings that mimic the slippery nature of the pitcher plant. This coating features tiny nano hairs, and these hold a thin layer of lubricant which mimics the presence of water on the pitcher plant. The company calls this technology the Liquid Entrenched Smooth Surface, or LESS for short, and it can easily be sprayed onto a variety of surfaces. Because LESS coatings make surfaces very slippery, it allows them to stay cleaner for longer, as they naturally repel fluid, dirt, bacteria, and even solid waste. This is particularly useful for things like solar panels and camera sensors, but also for reducing the harmful effects of using toxic cleaning products. It's even been used to create super slippery toilets, which repel human waste and save vast amounts of water. Thanks to the pitcher plant-inspired technology, these coatings have the potential to save billions of dollars in cleaning costs for all sorts of surfaces, which is great news for the planet, unless you're an ant.
Yeah, I guess this video sums up really well about some of the work we did for biomimicry. We look into nature, start with a particular biospecies, in this case, a pitcher plant. And you guys probably noticed a pitcher plant and a toilet bowl might look alike. Pitcher plant, they use a slippery surface to capture food source, in this case, ants. And for toilet bowl, if you put a slippery coating, you can remove waste more efficiently, and in that way, it saves water. So that's kind of how our lab started the nature-inspired engineering. We look into natural species, create new materials, and solve important global challenges.
Cool, thank you, Tak-Sing. Cece, can you tell us a little bit about Metalmark Innovations?
Sure. Yeah, that video is super fun, right? So Metalmark has a bio-inspired technology as well. Our inspiration came from butterflies, like the Metalmark butterfly, which is a really large family of butterflies and moths. And many butterfly species have nanostructuration in the wings, in the material of their wings, and that's what actually gives rise to a number of functions, like their beautiful iridescent colors that help them to camouflage and attract mates. They help to provide the strength and lightness to enable the butterflies to fly, and it's a water-resistant kind of material. And so our inspiration came from that. Initially, we were just trying to mimic colors that are found in butterflies. And my co-founders, who are the brilliant scientists, actually took this one step further and created catalytic materials from the structuration they found in butterfly wings. And lo and behold, by using this methodology, we can create very highly functional catalytic materials to break down air pollutants, and use this also in a number of other applications. And so that was how Metalmark got started, and we're targeting indoor air quality right now, particularly focusing on spread of pathogens like coronavirus and other toxic air pollutants like volatile organic compounds and ultrafine particulates.
Thank you, Cece. And Claire, could you introduce us a little bit to your work?
Yeah, I'm trained as a biomimicry professional, and that profession did not exist as a current profession until the first cohort of biomimicry professionals, which I was part of. And our role is to bring the practice of biomimicry into every field, whether it's engineering and technology, or architecture and urban design, or product design, reshaping the future of chemicals and chemistry, and rethinking even our future economies and organizational design. And I've been practicing biomimicry for over a decade now, both as an educator, because it's a new field, and we have to bring it into our education, whether it's at school level all the way through students at university into professionals, and to also design projects that start to bring biomimicry into existence, and to do research on behalf of companies, and to train companies and their staff to be innovative and to think differently about the way they solve challenges. But most importantly, to bring the ethos of biomimicry, which is the idea that we as a human species could be a welcome species on the planet and actually create technologies that nourish life. My one project that I have is the organization called Learn Biomimicry, which is an online platform where anybody in any field can begin their journey in understanding the ways that we apply biomimicry into any field. They learn the basic tools and the basic practices, and they learn the big reason why we do it at a systems level, and then the basics of how to do it at a process recipe level and at a product design level as well. And that's the main project that I'm representing here today.
Great, thank you. Thank you all. You're just all doing such fascinating work. I'm excited to have this conversation with you. You know, first off, it's clear you're all working to address this kind of sustainability, environmental, the environmental challenges that exist today. I'm curious, putting on the business hat, we have, I think all of you have companies or you work with companies to bring this to life. Why is your solution better? Why should people look to nature to design new products? So maybe Cece, I would love to hear how Metalmark is competing against some of the other alternatives that exist today.
Sure. I mean, for our technology, there are so many levels of bioinspiration that came together to enable this technology. But I think the first and foremost is that when we, as I mentioned, our inspiration first came from butterfly wing material. And so in these materials, you find a very simple material, which is chitin. And through structuring chitin in different fashion, you can actually achieve multiple functions as well. And this is a very powerful idea, because in nature, it's all about efficient use of material, using very simple precursors of materials to design a variety of things that we find around ourselves. So, for example, nature uses about 5 types of polymers, and we use about 350 types, and we're constantly coming up with new ones. And as Jara said earlier about nature, really, perhaps unintentionally, but certainly it designs in such a way to be sustainable and with life in mind. I think there's a lot of wisdom in that, in this kind of simple illustration that, if we actually structured materials simple materials in a variety of fashions, we can actually achieve multiple functions and create new technologies for ourselves. And that's, so when we think about what we do, so we use the ideas of structuration and apply that type of the structures that we find in butterfly wings to catalysis. And so creating similar structures used at the nanoscale, and we end up seeing a lot of new characteristics from the material, from it being a lot more stable. So our catalytic materials have been tested in very harsh conditions, aging conditions, to show that it's very durable and stable as a catalytic material compared to the conventional. We have shown very high activity with the material as well. And at the same time, we can very significantly reduce the amount of catalytic material used in the first place. So it is sort of this combination of efficient use, higher function that really brings so many value propositions to our product. And it's made possible because of the inspiration that came from nature, which is really evident all around us.
Yeah, I would definitely second Cece's comment. The butterfly wing is a beautiful example of nature, of how micro and nanostructures can give out brilliant, beautiful colors. And indeed, nature has over 3.8 billion of evolution history, with over 8 million natural species now identified on the planet. If you happen to stick electron microscope on any surfaces of this natural species, you will find a wealth of micro and nanostructures on the surfaces, and they use that for their daily survival function. For example, if you look at tokay gecko, they use their flexible nanostructures to adhere virtually on any surfaces repeatedly, which is something that a synthetic adhesive could not do. And another example, if you look at the moth eye, their compound eye consists of millions of nanoscale structures, which allows them to absorb visible light so that no light can be reflected off from the surface, so that they can avoid predator when flying at night. And because nature is really a master of nanotechnology, so my laboratory at Penn State have been really intrigued by this kind of nanotechnology. So that's why we have been looking into this kind of micro and nano structures on natural surfaces to create new materials. And the picture print example I just mentioned was a perfect example, because typically how biomimicry or bio-inspired engineers start a project, one way to look at it is to start with a specific biological species, for example, in this case, pitcher plant, and trying to understand how that works, why the surface is so slippery. And then we will use our current man-made or synthetic material to replicate this concept. Because as Cece mentioned, natural materials, there's only that many materials, but in the human world, in the engineering world, we have expanded this materials database to much more. So we can build a much stronger capability to create nature-inspired materials for different applications. And in our case, that is really how we can expand how pitcher plant repel plants to now create a slippery coating that can be put onto a broad range of materials, including glass, ceramic, and metals, to repel all kinds of the materials. And that is really the basis of the startup Spotless Materials that is currently commercializing an easy sprayable coating that you can put on different kind of materials to repel different type of waste, to save water, to save energy.
Yeah, and I think what's so phenomenal as you start to get into the field of biomimicry is many of us think these are new technologies, like nanotechnology is only a couple of decades old in the human world, but nature's been exploiting at the nano level for millions and millions of years. And so it's figured out not only how to make nanostructures achieve functionality that is really extraordinary, but to do so in a way that's life nourishing. I come from a field that is chemical engineering, and that field is really known for making huge amounts amounts of pollution. We make single-use plastics, we refine oil, we make herbicides, pesticides, all the chemicals that we are really worried about the use of and the effect it has on our environment. And what I've learned over the years of studying biomimicry is that every single material that we make, nature has an equivalent functional material that is low energy, uses carbon as a raw material instead of emitting carbon, and actually is so life friendly that it totally reintegrates back into the environment. Even if it is a poison, you never see a snake on the side of the road protected by a hazardous materials group team, because that snake, when it actually gets reintegrated and biodegrades into the environment, is totally life friendly. So as we're learning to be, high tech and quantum tech, it's really important for us to not just mimic that genius side of nature's technologies, but also to integrate that wisdom. When we make the equivalent of a spider's web, we make something called Kevlar. Now, Kevlar is a very tough, very strong, very flexible material, and it's typically used in boat hulls and in bulletproof vests. And as chemical engineers, we figured out how to make Kevlar with a heating, beating, treating recipe, which is to boil petrol in sulfuric acid at 750 degrees Celsius and then extrude it through very high pressure, leaving toxic waste and huge amounts of pollution in the process, but also using large amounts of energy and emitting lots of carbon in the fossil fuel usage. Now, the spider web recipe is made using dead insects and water at the temperature of the cold-blooded spider. And it is so life-friendly that the spider can eat it after it's spun that web. And the equivalent function, equivalent strength, equivalent flexibility, very low temperature, using carbon as a raw material instead of emitting it. There are so many examples that in terms of how much more we can improve our technology. So we often talk about how nature's tech isn't as efficient. So we might say a leaf isn't as efficient at photosynthesis as our solar panels are at capturing the energy of the sun. But our solar panels are made using fossil fuels, they're made using toxic chemistry, and they end up in landfill sites causing leaching. Whereas nature's solar panel use carbon dioxide as their raw material. They breathe out oxygen as they're capturing that energy of the sun. They're evapotranspiring at the same time, contributing to the water and rain cycle. And when their life is over, they become mulch or compost and then build topsoil. And so we might not say that nature's recipes are always as efficient, but they're highly effective and they integrate all of those externalities. And it's now possible for us through the fields of biomimicry to make polymers that use carbon dioxide as a raw material by mimicking the enzymes that nature uses, to actually produce materials that can become compost, and to actually start to think about how we can advance not just our photosynthesis by mimicking nature's our photovoltaics by mimicking photosynthesis, but to do them in life-friendly and constantly cycling ways. So yeah, nature does it better, not just in a high-tech way, but in a highly wise way as well, which is important.
Yeah. Thank you. Thank you all. And Claire, I think on that last point, at the Institute, we recently put out a report in the fashion industry called The Nature of Fashion, where we explore this concept of circularity and how in nature, things break down. It's always it's a cyclical cycle, and things are always going to leach out. It's not a perfectly closed loop. Like a leaf doesn't always turn into a leaf again. It's going to turn into many different things: animals, plants, fungi. And I think one of the really interesting things we're seeing in biomimicry is this whole concept of what does biodegradable look like? How do we design products that have that lifespan in mind, that realize that maybe we can't have a fully circular loop, and we have to design things with that kind of entropy, really, leaching in mind. So I think that decomposition is a really great pattern, and we touched on nanotechnology. Are there other kind of patterns that we're starting to see emerge? And I guess just to touch on that, now that we have tools like scanning electron microscopes, like you mentioned, texting, and this ability to create self-assembling structures, somewhat like Metalmark, are there patterns that are kind of in our reach, things that we should be paying attention to as we design our world?
Oh, maybe I'll jump in here and say that I completely agree with your point, Jared and Claire. It is, beyond just kind of getting inspiration from nature, and designing these very functional, cool new materials, we have to kind of pay attention to the sort of cradle to cradle types of implications of what we're doing. And so there's, the synthetic materials that are made have potential downsides to them, and we have to be intentional in thinking about how we design holistically. And so at Metalmark, one of the things that we are constantly thinking about is this idea of recycling, regeneration of our material. So it's great that we can put it out into the world and have it be used, but then what happens at the end of life? Does it get thrown away into landfill like everything else, or could we actually recover that and regenerate it or recycle it in some other way? And that's kind of fundamental to our thinking. And so I think that is sort of at the macro scale a challenge to engineers and scientists, and it's something that we can learn a lot from nature, and keep that in mind as we do R&D.
And that's very true. As a scientist, when we start developing a new type of bio-inspired materials, what kind of raw material that we start with is something that we think about a lot. Depending on the applications, a lot of time we will choose a raw material that can be biodegradable, for example, like what Cici was mentioning. Because at the end, like what is the end life cycle of that bio-inspired materials or product? So picking the right raw material to make those materials are a very important consideration for many scientists who are in this area of biomimicry and bio-inspired engineering. Because at the end of the day, if we can create a new engineered materials which they can function as we designed, and then at the end of their life cycle, if they can be decomposed or biodegrade into its natural form and recycle back again, that's really like the ideal way of biomimicry or bio-inspired engineering.
Yeah, and I mean, you did mention what are the patterns that we find in nature, and I know there's many specific patterns, but I'm most fascinated by the generic patterns that you see repeated in every single species that's on the planet, and we tend to call those life's principles, and the principles that are indication of a successful species, one that's likely to survive and thrive. And those are the ones that have not just met their own functional needs, but have integrated into the system that they're part of and contribute to nature and the larger system itself. And the kind of patterns that I'm fascinated by, yes, cycling all materials is a common one. Fitting form to function, so using the structure for functionality rather than the chemistry for functionality. And then having cooperative networks that are distributed across the system so that all materials can be manufactured locally and cycled locally in a local relevant context. And then there's a heck of a lot of diversity in doing all of that. So those kind of combinations of diversity for resilience, locally relevant. But my favorite one is making use of what's readily available materials, which nature tends to celebrate abundant materials by using more and more of those abundant materials and cycling them over and over again, like carbon, oxygen, hydrogen, nitrogen, most abundant materials in the world used in almost every single material that nature has. Whereas we tend to celebrate or value very scarce materials, like platinum and those really difficult ones to get. And so by us really just recognizing how do we actually value what's abundant, and how do we create that abundance by constantly cycling those materials and making them available again, I think that's a really important thing. But also nature uses, like as I said, 6 or 7 sort of basic types of materials: silks, biominerals, polymers, chitin, cellulose, but then just simply changes the structure from a macro form all the way to a micro nano form, just to achieve the functionality that we're looking for, whether it's a slippery surface or reflective coating or any function we want. What I love about the exploiting structure for function, it has a huge implication for pollution. So just that slippery surface that Tak Singh's worked on, if you replaced every single paint tin in the whole world with that surface in it, every time we ever use paint, instead of cleaning it with turpentine or water, causing large amounts of pollution, you just simply pour it out and it just drips off and you can reuse that tin. It's a huge, big impact on water and waste pollution. So that deep pattern of exploiting structure for function and making use of abundant materials are two of my most favorite ones that we found.
Yeah. And paint made me think of another solution that was inspired by butterfly wings, a company we recently worked with called Spotless Materials. And I think this is a great example of how these structures can inform a multitude of different solutions. Again, it comes back to that form. But this company, Spotless Materials, saw that butterfly wings, they're not pigmented. Those brilliant blue morpho butterfly wings, that's blue wavelengths of light reflecting off of those scales. And they have since created a paint that actually self-assembles to reflect those wavelengths of light. It's a process called structural coloration, structural color. So we're not using any pigments or dyes. Instead, it's how those wavelengths of light bounce back and reach our eyes. And they can do this across the UV, visible, and infrared spectrum, much like many animals bring structural color to the forefront. And maybe, Claire, structural color is seen throughout nature. Can you maybe give an example of some of the different species we see that in? So we have morpho butterflies and...
Yeah, so most of the blues and greens that you see in nature, they are made from structural color, not a pigment. So it's not a chemistry so much as a keratin layer, which is the same thing that all feathers and hair and nails and are made out of. But that final layer has a nano surface to reflect light, and it reflects those blues and greens. The peacock's feather, one of the most famous ones, it's actually brown until sunlight hits it, and then it creates that color. So the color is created through structure, not through pigment, which is interesting because a lot of the time we add heavy metals and toxic chemicals to dyes in textiles and even in paints in order to hold that color in place. Because if you've ever noticed your couch or your sofa might start to lose its coloration as it's exposed to the sun, your t-shirt. Whereas what's so amazing is what those creatures have done, like peacocks and macaws and butterflies, is they actually use the sunlight to generate the color instead of the sunlight leaching or losing that color. So there's many more. Then the reds and oranges and yellow pigments tend to be carotenoids and actual pigments, but the blues and the greens are structural color.
Maybe I'll follow up on that a little bit, because Metalmark, our technology, was also inspired by the same concept. In fact, because of the structuration in our material, you actually get really beautiful iridescence. So we have samples that are the purplish, bluish, and greenish versus the pinkish and reddish. And so by simply changing certain structures, so like we literally can use the same kinds of material composition, but structure them differently to have different coloration results. And that was actually the initial point of how we started. And it is still a really good representation of whether or not we succeeded in each product batch to create the structure that we wanted. So it's such a powerful way to make materials. And I would also say that to Claire's point about fading of colors, of chemical pigments, if you take a butterfly wing or a feather that is iridescent to begin with, and you kind of preserve it, right? Just maintain the structure of the material. It can be preserved for a very long time. So we can go to natural history museums and see these very old or even extinct species that represent this so well, right? So it's just a strong and efficient and multifunctional approach to nanostructure materials.
Yeah, I think Clara and Cici, they mentioned a number of really beautiful examples of how nature uses structural colors to reflect different visible light. And there's another class of also is like a structured color, but instead of reflecting light, they use those structures to absorb light. I have in my lab at Penn State a couple of years ago, we looked into this species called leaf hopper, are tiny insects that live on leaves. And one amazing thing that they do is they secrete this nanoparticle called glucosome. This glucosome looks like the patterns looks like a soccer ball. It's a microscale sphere with some nanoscale indentation or nanoscale peat surrounded around the microsphere. It looks like a soccer ball or carbon-60 for those chemists who know those carbon structure. And so this leaf hopper secrete this glucosome, and then they rub these structures on their surfaces or on their newly laid eggs. For a long time, scientists didn't know why they would do that. Recent work showed that this glucosome water repellent, meaning that this leaf hopper rub these particles onto their leaves to prevent them from sticking to the moist environment that they're living in. But they also rub this soccer ball-like microparticle onto the newly laid egg. So recently, our group discovered that the nanoscale indentation is designed in a way such that it can absorb most of the visible light. And there's a reason for that, because if you can absorb most of the visible light, and if you cover it on top of the newly laid egg, it does serve as a camouflage purpose so that it can blend into their background, so that predators such as their birds or even ladybird beetle, they wouldn't be able to see them, because this species, they are sensitive to both visible and UV light range. So the glucosome structures, their patterns is able to absorb the UV and also visible light, so that the leaf hopper can help to protect the newly laid egg against those predators. So this is another example of how nature uses nanostructures to absorb light instead of reflecting light for survival purpose.
Oh, that's so fascinating. So one of the questions we get frequently at the Biomimicry Institute is around intellectual property, kind of legal issues. If these systems and forms and technology exists in nature, can we protect that? And should we protect that? And part of that is critical to making a new company or bringing that into corporates and businesses. So I'm curious for all of you, how do we address that? And Claire, maybe with your work with companies, is that something you can speak to?
Yeah, I think the most important thing is you can't have a patent or IP on the actual natural organism. You can abstract the core principle that you're interested in, and then you can design a particular product, process, or system based on that principle, and then you can protect that product, process, or system. You cannot protect the organism. And the Biomimicry Institute has worked to create the asknature.org website, which is a living library of all the things we're learning from the natural world. And because it's now open and in the public space, it's kind of helping to kind of be ahead of the game in making sure that that information was in the public space first. It is from nature, so therefore you cannot own that information. So it's a freely available source of biological information, sorted according to function, what we can learn from it. And it's called asknature.org.
Yeah, thanks, Claire. Yeah, that's a great resource. And it kind of touches on another point is we have two examples that kind of came out of academia, this deep study of biology or biological engineering. But you don't have to be a research scientist to bring biomimicry into practice. Yeah, I would love to hear maybe an example of how biomimicry has been brought to the table by designers or by engineers. I'll think of some, but do any of you have any in mind? That's okay.
Yeah, there's tons of product design examples. Many of them, from Velcro, the most common one that people are aware of in the biomimicry world, to the leading edge of the Shinkansen bullet train, being shaped like a kingfisher, to a toilet bowl that was shaped mimicking the vortex that water flows in, that's just called the Arum Blue. Many product examples, and then there's many sort of process examples, like a forward osmosis system rather than reverse osmosis, that mimics the way that mangroves and kidneys draw water out of salt water. And then there's quite a few ideas at sort of the mimicking systems level, which are the eco machines or living machines that mimic wetlands. So many ideas. In the architecture world, so many extraordinary biomimicry buildings coming out of the work, like from Mick Pierce, who was one of the first to design the Eastgate Centre in Zimbabwe, mimicking the way termite mounds keep themselves cool. And Michael Pollan's quite a well-known architect who's written a book on biomimicry and architecture, and then an extraordinary architect from Belgium called Vincent Callebaut, who's designing visions of what the future would look like if we designed a world that nourished all of life, and if our cities actually integrated nature and functions of life in the way they design things.
Yeah.
Wow.
And certainly, maybe some of the micro robotics that are occurring right now in mimicking some of the soft materials that are found in organisms, as well as the sort of organizational behavior of beehives and other that are fascinating to try to mimic from a robotics level. I wanted to go back to the IP question, Jared, you brought up really quickly. I would say that there is definitely no sort of IP issue in copying from nature, but as you already illustrated, companies like or researchers are working on mimicking similar types of phenomenon from nature. So, for example, cypress has a structural color material, and our inspiration came from structural color as well. So there's going to be, I think, competition from that perspective, just a lot of people starting to work on them, which is really exciting. So you can see that there are so many different approaches to getting to the same type of results. And then you can go beyond that by taking the inspirational concepts as the first step, and then apply that towards additional additional types of use cases. So it's a really exciting time to get into mimicry, I think.
Another example that not on the optics but more on the liquid repellent side. For example, lotus leaf is known for its water repellency, and there are a number of products, including lotus sand paint, that are roll off, commercialized for a self-cleaning paint. For example, the pitcher plant inspired surfaces, there are also different products come out. For example, the adaptive surface technology rolling out from Harvard, Spotless Materials are rolling out from Penn State. All of this are mimicking pitcher plant type of slippery surfaces, also for liquid repellent and solid repellent functions. So yeah, so like I think mimicking from one species, there are many new concepts that can come up with using different type of materials to create different type of product with different concepts. So yeah, it's a very interesting and very broad field that people can learn from.
Yeah, it's how we're adapting it to meet kind of this human designed world, which is fascinating. Well, we asked a poll question, which was, can nature inspire a radical redesign of our systems? And I'm happy to say 100% of you said yes, which is great. I want to close by maybe each of us just sharing just real quickly, like a vision for what our world could look like if we continue down this approach of nature-inspired design and biomimicry. You know, for me, it's seeing more products and companies that are bringing to market solutions that are inherently sustainable, things that don't rely on petrochemicals, synthetic chemicals, and things like that. But yeah, for all of you, what does this world look like?
Yeah, I wanted to share that actually on the Learn Biomimicry online courses, such as learnbiomimicry.com. There's a module on what biomimicry is and how to do it. There's a module on these deep principles that we find in nature, but the final module is about what would our whole world look like if we redesigned every system, from water systems to material systems to energy systems, to organizations and even economies based on biomimicry. And I think there's a lot of detail in that, but it has the potential to shift all of them to nourish life and be more resilient as well.
Yeah, I echo all of that. Yeah, I mean, I think I've spent a long time of my career on the sustainability issues and looking at climate change solutions, and that extends to health and welfare of humans and how we interact with our planet. And so as we become more crowded on this planet and we face larger and larger challenges, as recently illustrated by the pandemic, I think we can only look to more technology solutions to kind of speed up our sort of transition to sustainability. And it takes a lot more people with this kind of mindset about, not just thinking of inspiration from nature, but from a technical perspective, but also the sustainability, the overall life cycle perspective to get us there. So I'm really excited for the future and for being a part of this.
Yeah, and I think the common goal of all technologies is ultimately improving life and make our place more sustainable. And biomimicry is definitely a way of learning. And also, if people can apply biomimicry creatively, there are more technologies that are really out of our imagination that we can create, and really the sky's the limit.
Yeah. Well, thank you all for joining us. This was a fantastic conversation. We had CC Liu from Metalmark Innovations, Taxing Wong from Spotless Materials and the Wong Lab at Penn State, and then Claire Yanish from Biomimicry South Africa and Learn Biomimicry. So hope you all continue to explore this topic. And with that, I'd like to pass it back off to Tabitha.
I absolutely loved what you guys just said. I think especially every time I look at anything, I'm going to start thinking of that kind of Kevlar spider example. You said nature has an alternative to everything. We just need to listen to the wisdom harder. And I'm definitely not doing that enough. So I'll be, I've already been, I think, quite changed by your session. So thank you. And I know you're all sticking around for the Q&A in 15 minutes time. So you guys can go and get a glass of water and we'll see you at 2:00. And the audience, you can also go and take a moment. And then if you are on the CogX platform, you can go ahead and ask your questions. If you're watching now on YouTube, head over to cogx.co and you can sign up at no cost to you. And for those of you who are waiting in your seat for the X Prize session, we will see you back at 2:00. Thank you very much.
Want access to more CogX videos? Subscribe now for free at cogx.co.